just a very brief review of what we covered on Tuesday. Okay, so on Tuesday, we'll talk about how to solve LP problems graphically. And if we have only two decision variables, then we will be able to draw them on a coordinate system. And so let me ask you a few questions. So once we have the model, what's the first step to solve it graphically? We determine what? The feasible region. Good. We determine the feasible region. Okay. And what determines the feasible region? Which part of the model determines the feasible region?
The constraints.
The constraints. Okay. And so what do? You change those constraints to equations if they are inequalities, and you draw the lines. Okay. And when you draw the lines, after you draw a line, you decide whether it's the area under or above it. Okay. And if it's less than or equal to constraint, it's under. Okay. Sometimes the student gets a little confused. Say if the line is like this, so it is this area is under. Okay. Or the line is like this, then it's still this area is the under. Okay. And we said that make sure you look at either x1, x2, which one is on the vertical axis. The one on the vertical axis, you want to make sure when you look at the constraints, the variable that's on the vertical axis need to have a positive sign before you decide whether it's area above or under. Okay, if it's negative sign, then that's if for example in that specific constraint, this one, okay, that's an equal to 3. We'll say that. If it's this one, then it's the area above. It's not under because it's negative sign. Or the other way would be you change it to a positive, and then the sign change direction. Okay, so then it's above the area. Okay, so make sure you change it to this way, so it has a positive sign before you determine whether it's area above or under. Okay, so once you have those constraints, you define the feasible region. A feasible region means all the points in that region are a possible feasible solution to the problem. Okay, so once you have the feasible region, if we're going to use one of the methods, which is level curve method, what's the next step? Or let me ask you, what defines the level curve? Which part of the model? You use the constraints already, right? Okay, so the next part will be your objective function. Okay, and you use the objective function to determine the slope of your level curve. Okay, once you determine the slope of the level curve, then you can basically just draw one of the line using the slope and keep moving outward or inward to see whether it improves your objective function value, which is the intercept on your vertical axis. Okay, and at that time we need to make sure whether it's a maximization problem or minimization problem. And the sign of the objective function also the signs of the coefficients of your objectives decision variables are also determines that. Remember we had there's one slide. Make sure you look at that. That's one slide that tells you, okay, if it's in this quadrant, this quadrant, this quadrant, this quadrant, how do you move? Like you move in this direction, depending on the signs of your coefficients in the objective function. Okay, so that's the graphical solution. And the other way is so there are two methods we'll talk about. One is using level curves. Okay, and why they are called the level curves? Why those lines are called the level curves?
Because they're straight.
What's that?
Because they're straight.
They're straight, okay. Because they are parallel. Okay, they are straight parallel lines because they have the same slope. Okay. Then another method is let's see, one of you suggested that. Enumerating the corner points. Okay, so the other way. But under which special situation enumerating corner points won't work? Which situation? The enumerating corner points won't work in all the situations. There's one that won't work. Think in the way when you enumerate the corner points, what if there's no corner point? Can you enumerate it? Okay, so think in this way. Then that means which situation? Unbounded. Good. So if the problem is unbounded, that means there's no corner point in a specific direction, then that method won't work. Okay, and that leads to the special situations. So we talk about unbounded problem, which means you want to find the optimal objective function value or optimal solution. The problem just goes to positive infinity when you try to maximize it, or goes to negative infinity when you try to minimize the problem. Okay, what are other special situations we talk about? Redundant constraint. Okay, a constraint that does not play a role in defining your feasible region. It's outside of your feasible region. Okay. Any other special situation?
Infeasible solution.
Infeasible. Okay, you can find an area that satisfies all your constraints. Okay. Anything else?
The alternate solutions.
You have alternative solution. Okay. When your level curve's slope is the same with one of your constraints that happens to define your optimal solution. Okay, so the overlap and the part that overlapping area, the overlapping line is at every point on that line. The overlapping part is your optimal solution. Okay. Any other special situation?
When your feasible range is along one line.
When your feasible region is a line, becomes a line. Okay. When will that happen? When your feasible region is basically a line. When will that happen?
So equals to something.
Okay, when you have an equation in your constraint, right? Okay, when you have an equation in your constraint. If you have more than one equation in your constraint, what happens? When you have more than one equation, the feasible region becomes a point, because with two lines you define a point. Okay. Okay. What's that?
Very quick.
Okay.
Find it real quick.
Yes. Okay, so any other situation we didn't cover? Didn't cover all of them. Okay. Now, today we'll talk about the other method to solve LP problems. So the graphical solution only works if there are only two decision variables. Okay. Like if there are three decision variables, you can still do it. You can probably graph it in MATLAB mathematical software. But if there are like more than three variables, it will be hard. And there are other methods. So we'll talk about the general graphical solution, and the other one is the heuristic approach. We'll talk about this today. A heuristic approach is a rule of thumb for making decisions that might work well in some situations. Okay. Well, for example, we'll use the transportation problem. We'll try to solve it based on your experience, and just thinking logically, we'll solve it manually. So that's the transportation problem. Okay, and we formulated it. Those are the distance between each pair, and we have the Bushel amount available and the capacity. And remember, we're trying to minimize the total distance, Bushel distance. Okay, so remember that's the objective. I'm sure everyone can solve this. Okay, remember the objective is to minimize the total distance, Bushel distance. And when you look at this, if you're the manager and you don't have solver on you, okay, you don't have solver, and you don't have the solution, where will you start first? Which ones you are going to ship first? Which one? Which one?
The ones with the lowest distance.
The lowest distance. Which one is that? This one, right? Is that this one? Okay. Yeah, so because we're going to minimize the total Bushel miles, so we're going to start from here. And we're going to say that's Orlando, Clement to Orlando. Okay. And how many do we have here? So the Bushel available here, we can look at here, it's 3,000. And the capacity here, it's 300,000. And here. So we'll just say, let's just ship 300K for now, right? Just use up all of them. And here, then you still have what? 300 capacity left. Okay, then where do you go next? Did everyone get why we choose this one? Okay, okay. Then next one we go to here, right? We go to the next least distance one here. So this one, this 21 here. And we look at the capacity and the availability of the supply. we found, okay, capacity is 200K, so we'll just use 200K. And here we still have like 75,000 left. Okay, and then we'll just keep going. The next one would be this 22 here, right? 22. We'll look at, okay, so the capacity is 225. And so here we're ending up with 175 from the 400. Okay, and this one is gone. Okay, this one is gone. And then we go to the next least distance, which is this one. But this one we found out, okay, the capacity is already used up, right? So we can't do this. Then the next one, 30, which is, which one? Eh, did I, oh here, okay, so this one we have 175K capacity, supply, and now this one is changed to be 125, okay, and then we go to the next one, 35, oh, but we go to this one, the 35, but we see that the supply is already used up, so nothing here, and the capacity used up too. Anything else left? So we go to the 40. This one, capacity is used up, so we can't ship anything there. 40, then we go to 50. 50, we still have 75 available, so we'll put the 75K here. That's here, okay, the 75, and we have 55K capacity left. And we go to 55, that's already used up. So that ends up being our result. Okay, 275, 175, 225, 300. That's the heuristic approach that we try to use to solve. And then let's compare this to our solution. Our solution is different. It's 200 here, okay, that's the same, but 0 here. Oh, and the 250, 300, 225, and we had this one. I'm not going to calculate the total distance, but this one, the one that got solved using solver, actually has less total distance bushel miles than the one that we just calculated by using heuristic. Okay, that means while we're solving that, we missed something there. Okay, so that's one thing need you to remember about heuristic, is that heuristic approach does not necessarily return the best optimal solution. Okay, and but sometimes, especially if the problem is nonlinear, if it's nonlinear, at the end of the semester we'll talk about that. There's many times we won't be able to find the solution, and heuristic may be the only way to solve a problem. Okay, but in those LP models, heuristic does not necessarily always give you the optimal solution. Remember we solved the TV newspaper ad problem? We worked on the board finding out which one is the most efficient, and we feel that. And in that specific case, the way that we solved, it's a heuristic again, but that gives us the optimal solution. Okay, so it's like you never know. It may be or may not be the optimal solution. So that's a rule of thumb and does not guarantee optimal solution. Now we'll talk about simplex method. So this one, it's excuse me. So the book does not have a specific chapter about the simplex method, but it's a method that you need to understand how it works, and we'll just give, we'll have a few problems on it. There will be a homework on it. So if you can follow me, when we start to do the works, I'll ask you to follow you. I'll ask you to follow me. Okay. You can either use your Excel. Using Excel will be easier, but you can work on just like the paper too. But I'll talk about how the method works generally, and then we'll do some work together. Okay. So the simplex method is used to identify, like the other Martin asked me whether we can use like the way we solve like algebra to solve the equations. And we said, well, when we have specific number, like I say, we have if we have 5 variables and 5 equations, we will be able to find one set of those values for the variables. Okay, but in our situation, like in the, a lot of those LP models, we usually have more inequalities in the constraints than the number of the decision variables. Okay, so that means, and we illustrated in the graphical solution, there are more than one solution that will satisfy those inequalities. And the purpose is to find the one that gives us the highest objective function value. And the simplex method is we convert those inequalities in your constraints to equations so that we try to solve them, and we find which way we go will give us the better objective function. Okay, so this is how we convert the inequalities. Okay, if we have less than equal to constraints, okay, here. So that's something you need to remember. If we have less than equal to constraints, we will add a slack variable there. Let me change my color. Okay, so if we have a less than equal to constraint, we add a slack variable. Okay, and if we have greater than equal to constraints, we subtract an excess variable. Okay, so this is called a slack variable, and this one is called the excess variable. And you can see that the slack variable or excess variable, they are basically the difference between your left-hand side and the right-hand side of your constraints. Okay, later when we talk about the sensitivity analysis, that's what the sensitivity analysis report will give you, the excess, the slack or the excess. In the sensitivity report, they call both slack, but like one would be positive, one will be negative. Okay, we'll use this model as an example. Let me just write it down here. So we have the reference here. So we want to maximize 250 x1 plus 300 x2 subject to x1 plus x2 equal to 200 x1 plus 6x2 equal to 1566 and 12 x1 plus equal to. Okay, those are both greater than equal to 0. So that's our model. And what we're going to do is to translate this problem. Okay, I'll go back here. So we said that for less than equal to constraints, we're going to add a slack variable. Okay, and all those variables we add, like the slack variable, excess variable, they are all positive. Okay. They have to be positive, otherwise your previous, like your inequality won't be valid. So now we translate them to this way. So you compare this. This is less than equal to, so we add the slack variable S1. Okay, we add the S1 there, and the second constraint, again, less than equal to constraint. So we added another slack variable plus S2 there, and the third constraint. So in this specific model, all the 3 constraints are greater than equal to constraints. That's why we added those 3 slack variables to convert those inequalities to equations. And then we add here. We make sure that S1, S2, S3 are positive. Okay. This is a very, now it makes perfect sense, right? Because if later when you calculate your S1, S2, if it becomes negative, what does that mean? If for example, if S3 is negative 10, if this is negative, what does that mean? That means your 12x1 plus 16x2 is what? Is is 2,890. So it's not less than equal to 2880. Okay, if this is a negative 10. So we want to make sure. And but many students miss that, and when they solve the problem, they had some negative slack variable values. They didn't find that they didn't catch that as a sign of error. Okay, but make sure you check it once your problem is solved. Check to see if all your slack variables or excess variables are positive. If they are not positive, that means something wrong in your calculation. Okay. Okay, now we have those equations now. If there are n variables in a system of m equations, where n is greater than or equal to m, okay, so meaning we have more variables than equations, we can select any m variable and solve the equations, and set the remaining variables to be 0. Okay, so now we have, in other words, we have more equations than the number of variables that we can, let me see. No, actually, here we have 1, 2, how many variables we have? We have 5 of them. Okay, after we add the slack variables, now we have 5 variables. And how many equations we have? 1, 2, 3. We only have 3 equations. Okay, if we have 5, then it's simple. Then we can just solve. There's just one set of variable values. But here we have more variables than equations. Then what we're going to do is select any m variables. So what's the m value in this case? What's the m in this value? Are you guys following? How many say 3? What's the m value? M is the number of equations. So, yes? 4? Okay. Well, we're not going to count the last one. Yeah, you probably counting the last one or the object function. We don't count the object function or the non-negative constraint. Okay, 3, good. Yeah, so we have 3 equations, okay? And then, so that means we're going to select 3 variables among those 5. What?
I'm good. I just sneezed, sorry.
Okay. Okay. So we have 5 variables, okay? And we're going to select 3 of them to solve. And set the rest of them to be just 0. Does that make sense? We just set them, it's kind of like we just choose the rest of them to be 0 and then solve the rest, which we have enough number of equations to solve. Okay, and that will give us one set of decision variables value. And we'll see, okay, whether that's optimal or not. If it's not, then we're going to keep change. We'll switch. Okay, so now it's kind of like this. Those first 5 representing feasible solutions. Okay, for example, in this first situation, we said, okay, let's just choose 3 to solve. Okay, we're going to choose S1, S2, S3 to solve. And we're going to set the other 2, which is X1, which are X1 and X2. We set those 2 to be 0. And then we use the 3 equations to solve S1, S2, S3. Then it's pretty simple, right? We set those to be 0. We're going to use these 3, okay? After we set X1, X2 to be 0, what's your S1 value? 200, right? And X1, X2, 0. S2 is 1566. These 2, 0. S3 is 28880. That's a feasible solution, right? Which point does it represent? Our coordinate system. You guys remember in the graphical solution? If it's 0, 0, remember our feasible region, something like this, right? And this point, X1, X2 both 0. So that's this point here. It's one of the feasible solutions, okay? So now we're going to say, okay, but it is feasible, but is it optimal? No, we're going to switch. Okay, so then what about we switch one of them? We say, well, so this is like the way simplex works. Okay, then we say, okay, we're going to just go from this point. And we know from the graphical solution concept, we know that the optimal solution always happens at the corner point. So we're going to do from this point, let's go. We don't have to check all those points in between, okay? We're going to go this point or this point to see which one gives us better, which one improves our objective function better, okay? Then if we switch to this one, then that means we are setting this x1, this x2. If we switch to this point, which decision variable we are setting to be 0? If we, x2, okay, so we're setting x2 to 0 now. And we're going to switch one of those s out. Okay, so like from here to here, it's kind of like we switched x1 and s2. Okay, let's solve for x1, s1, and s3, and we're going to set x2 and s2 to be 0. And those ones that we set to be 0, we call them non-basic variables. Okay, and the ones that we're going to solve, we call them basic variables. So the basic variables are the ones that we're going to solve using the equations that we changed from the inequalities. And the rest of them are none. And then we just keep going. For example, as we come to this point, and in simplex, we'll talk about how you decide. Is that this point or this point? So you always move to an adjacent point, okay? There's no way for us to move directly to this optimal solution. But we can always say, well, let's start from this point, and we determine is going this way or going that way gives us more improvement to our objective function value. Okay, we determine which way gives us more improvement. Then we go to that direction. Suppose this way gives us more improvement, then we come to here. And when we are here, we look at our objective function. We look at, in simplex, there's a way to tell. I'll tell you how to do that. We look at is that optimal or not? Can the objective function be further improved or not? If it can, whether it's this direction or this direction. So you will look at it again. Sometimes you may switch back to the point that where you went. That's called like a circling in the algorithm, and that's like a special situation in it. We'll try to avoid that. Sometimes when you have like zeros on your right hand side, you may circle back to a previous solution. Sometimes you just keep circling there, and that's one of the problems that the algorithm will have. Okay, but like in this case, you look at okay, this way, moving this way will improve the objective function. And then you keep here. This is like a 2 decision variable. If you have more decision variables, there will be like more directions to go. Okay. And then you look at here whether the objective function value can be further improved. Yes, no. If yes, keep going. It's this direction or this direction. If no, then we stop here. That's our optimal solution. Okay. That's kind of like how the algorithm works. And now we're going to talk about how do we do that. So we identify any basic feasible solution or extreme point, then move to adjacent extreme point if such move improves the value of your objective function. Then moving from one extreme point to an adjacent one occurs by switching one of the basic variables with one of the non-basic variables. Okay, like we switched the S2 out and switched X1 in, okay, to create a new feasible solution. And then when no adjacent extreme point has a better objective function value, we will stop there, and that the point is the optimal. Okay, so now the specific procedure. We'll convert the LP to a standard format, like changing the constraints to equations, and we'll also convert the objective function part. Okay, we'll obtain a basic feasible solution, meaning, for example, we'll start from 0, 0, 0, the 0 point. So we know that this is a feasible solution. We start from here, and we start to switch. Then we determine whether a current feasible solution is optimal. If it is not optimal, determine which non-basic variable should become a basic variable, meaning how do you switch, which one do you switch in. And then use the elementary row operation that you learned in algebra to find the new basic variables. And then go back to step 3. Okay, so now we'll do this one. So here you can follow. This one, we have 3 variables. Okay. I'll ask you to convert the constraint first. So we have, I think I have that on the slide. So. Okay, so convert the constraint yourself. We're going to put maximize, and we'll give the objective function. We'll say maximize. Okay, maximize z. Okay, which equals to be the objective function plus 30x2 plus 20x3. Okay, we're going to maximize this, and the subject to, we'll let you convert the constraints. Done? Remember the last, remember to modify the last constraint to add all the select variables. Okay, done? You're done, you can look at mine to see. Okay. So we change the first step. So this is called the standard format of the LP simplex. We add another variable to represent our objective function. So I maximize this z equals to be your objective function. Okay, and then subject to the constraints, because in this model, all the constraints are less than equal to. So the less equal to constraints are much easier to work with than the greater equal to and equal to constraints. The greater equal to constraints, later we'll just talk about them, and you will appreciate how easy this is. Okay, this one, so use the less than equal to, we add the select variables. So add 4 of them, okay? And then we said, okay, we say all the select variables that we added need to be greater than or equal to 0. Then the next step, we have, since we now have, how many? 1, 2, 3, 4, okay. We have 4 equations, okay? And how many variables do we have?
2.
No variables.
6.
Oh, 6.
We have 3x, right? And 7s. Okay, so we have 7 variables and 4 equations. Then let me ask you, how many basic variables should we have? Basic variables are the ones that we're going to solve. Non-basic variables are the zeros. So how many basic variables should we have?
4.
Why?
There's 4 S's.
Because there are 4 equations, right? Okay, because there are 4 equations, so we're going to solve for 4 basic variables. Okay, because we have 4, and because we have 7 of them, so we're going to say 4 of them are basic variables, and the other 3 are non-basic variables. What's the value of non-basic variables? 0. We set them to be 0, okay? So we can solve the other. Okay. So starting from the origin point, okay. Origin point here means x1, 2, 3. We need 3 of them. So x1, 2, 3, they all be 0. Okay. So we'll set x1, x2, x3 all be 0. And then we solve for s1, s2, s3, s4. These are the values. Those are non-basic variables. And our objective function is 0. Is this optimal? For sure not, okay? Because we want to maximize it. Okay, so now we're going to, so I'll talk about the step, then we'll use Excel, okay? So the next step would be, we'll convert the objective function into a row 0. So we use a table to do this, okay? Row 0 is the objective function, and we're going to move the right-hand side of your objective function. So we're going to move this side to the left. So that's the z subtract your right-hand side equals to be 0. And we'll put the equations including the objective function, the converted format, into a table. Specify the row number, coefficient of each variable in each equation. So earlier we had 4 equations, plus this objective function, we have 5. Okay, so we're going to put 5 rows. Each row we will put the coefficient of each variable, the right-hand side value, and the basic variable in that row. And now we're going to, and the z, S1, S2, S3, and S4, those are basic variables. So including z, because once you have values for all your variables, then you can calculate your z, your objective function, which is 0 in the case. And x1, 2, 3 are non-basic variables, they are 0. And we're going to decide which non-basic variables, so the x1, 2, 3, to increase or to be changed to be a basic variable, so its value will increase from 0 to a higher value based on the impact on the objective function. Okay, so now I'm going to go to Excel. We used to just draw on the board, but I think we'll save some time using Excel. Plus, I don't draw really straight on the board, so Excel helps me. Okay, and you don't need to do the calculations. When you do your homework, you can use Excel too. Okay, so those calculation, but not using software. Okay, you need to show the steps. Okay. Okay, so now we're going to put. I'm going to sit here. So we have, we're going to create this table here. This is the one. Yeah, okay. So we're going to put a row number. We'll set up the header of your window, of your table, okay? Then z, or all the variables will list them, okay? In that case, we have z, x1, x2, x3, then s1 all the way to s4. So we're going to list all of them in your Excel. x1, oh, jumped here. So x1, x2, x3, and we have s1, s2, s3, and s4. Okay, so those are our variables. All the variables will list them. I'll enlarge this a little bit. Okay. And then from the instruction, we say, okay, we're going to put which one is the basic variable in that row. So we're going to put, say, okay, the basic variable. Later, we're going to specify here which one is it, okay? And we'll put the right-hand side value. Yeah, so that's the heading of our first table. Okay, then we're going to put our model in this table starting from this row 0. Okay, so row 0, 1, 2, 3, 4. And what we're going to put there are only those coefficients. Okay, so for example, the first one, we're going to convert, we said we're going to convert it. So let me just convert it here. Once we convert this one, this one will be z minus 60 x1 minus 30 x2 minus 20 x3 equals to be 0. Okay, so that's our row 0, the actual row 0. And in the table, we're only going to put the coefficients of our variables in. So then you can see that the coefficient we put in will be 1 for z, negative 60 for x1, negative 30 for x2, negative 20 for x3, and the 0, 0, 0 for s1, 2, 3, 4. Okay, we can just skip them. Keep this one. Okay, we said the row 0. Okay, and I usually use a parenthesis to put this. So to differentiate. Okay, and we need to format this. Let's see. I need to format this row as a text. Okay, so now I can put just the row 0. Try to follow this, okay? Okay, then we said the z coefficient is 1, and 6, negative 60, negative 30, negative 20, and s1, 2, 3 from 0, they are 0, we'll just leave them blank. And the basic variable for this row is z. It will always be z because z is the objective function that we're going to try to solve. And the right-hand side value is 0. So that's from our okay, here. Find my mouse. Okay. Okay. This one I'm going to just copy it. We have 4 equations, so 1, 2, 3, 4. Okay. And this one will be row 1. Okay, now we'll start to put row 1. Row 1 is our first constraint. This one. So we're going to just put the coefficient here. Okay, we have x1, 2, 3, s1 coefficient. 8, 6, 1, 1, 8, 6, 1, 1. Z is 0. So 8, 6, 1, 1. Okay, and nothing for s2, 3, 4. The basic variable, we're going to leave it for now. The right-hand side value is 48 from the model here. Okay, And then we'll do the second row. Second row is 4, 2, 1.5, 0, 1. Okay. Any questions here? No. So the second one. 4, 2, 1.5. S1, there's no S1 in this equation here. We have S2. So it's 1 here. And right hand side value is 20. Okay. And this is row 2. Row 3. We'll finish entering this or take a break. Okay, so then 2, 1.5, oh, 1.5, 0.5, S3 is 1, 8. Okay, now the last row. The last one, the last constraint is basically S2 plus S5 equals to be, S2 plus S4 equals to be 5. So S2 have a coefficient of 1, okay, and that's it. S4 has a coefficient of 1. So it's S2 coefficient of 1 and S4 coefficient of 1. And the right hand side is 5. Okay. So that's our first table. Okay, so once we have this first table, the next step is to look at whether the objective function or optimal. The next step is to put the basic variables in. Okay, and we said in the first case we'll just use the origin, which is we're going to use x1, 2, 3 being 0 and s1, 2, 3, 4 being the basic variables. Okay, and the reason is if we look at here, the coefficient of s1 is 1 in this row here and 0 in all the other rows, and s2 here, s3, s4. And in linear algebra, if you have or a matrix, when you have a matrix like this, 0, 0, 0, 0, 0. So when you have a matrix like this, diagonal is 1, okay? And S1, S2, S3, S4. When you have two matrices, you multiply them together, and that's the right-hand side. So we do have the right-hand side, which is 48. Okay, so when you have these two matrices, this multiply this one equals this. That's what we have here. If you look at this side, okay, it's this one. This is the one matrix, and you have some basic variable here. That's on the right-hand side. Then what does that mean? It basically means S1 equals to be 48, S2 equals to be 20, S3 equals to be 8, S4 equals to be 5. Okay, like when you solve equations, that's the final format you try to get, right? Okay, so now we already have it. So that means from this table we can read S1 just equals to be, if we just put S1 here to be this basic variable. Okay, so our S1, we'll choose S1 to be the basic variable in the row where it has the coefficient of 1. And the coefficient of it will be 0 in all the other rows. Okay, so now here, we'll put S2 here, S3, and S4. So that's our first table. And from this table, we can also read, because you can read the Z too. If we look at this row, Z has a coefficient of 1 in this row, and all other rows is just 0. So that means we can also read Z equals to be 0. I can just add it here. Basically add one more row here. Make it larger. So Z what do we have here? 0. And we don't need to look at, like, those ones, those x1, 2, 3, they have some coefficients here, but it doesn't matter because their value is just 0. Okay, so we don't really need to read that. So that's what we get. So from here we say, okay, our current object function value, the current objective function z is 0. Okay. Z equals to be, we're going to move those back again. Is 60 x1 plus 30 x2 plus 20 x3 plus 0. So what I'm doing here is to move those ones. Move those ones back to the right hand side again. Plus this 0 here. So the current objective function, that's objective function, okay? And the basic variables are S1 equals to be 48. Oh, actually, we can just say the variable, the decision variables, but we'll separate them this way. S2 equals to be 20. S3 equals to be 8. S4 equals to be 5. Oh, this way. Okay, and the decision variables are x1 equals to be x2 equals to be x3 equals to be 0 because they are non-basic. The current objective function value is 0. Okay, so that's what we can read from this table. And after we read this, we're going to determine whether the objective function can be increased. Okay, I'll let you finish this one. We'll determine whether objective function can be increased, and if yes, which one? Which direction? So you see, we're basically reading from this side. Z equals to be 0, S1, S2, S3, S4. Any variable that's not here means they are non-basic and they are just 0. Okay. And now we'll look at here. Okay, let's see. Can we improve our objective function? We'll look at the objective function here. The objective function is a big positive value coefficient multiply x1, another one x2 plus x3. And we know that in the current situation, x1, 2, 3, they are 0. And if we switch one of them to be a basic variable, which means they will become positive, okay, will that improve our z value? We are doing a maximization problem, okay? Now they are all 0. If we increase x1 from 0 to any positive value, will that increase our z? Yes, it will. What about x2? It's 0. If we increase to positive, it will increase this one. Same with x3. Okay, now we have 3 choices. Which one should we choose? We only switch one at a time. And we know we're going to maximize our objective function. So we choose the one that gives us the highest impact. Which one gives us higher impact? X1, right? Because it has the highest coefficient. So that's how we decide. We're going to decide to switch x1 to be a basic variable. Okay, and then we need to decide we have all those 4 here. We'll never switch Z, okay, because D is the one that we're going to solve. If we switch it out, there's no point. We'll decide whether we switch S1, S2, or S3, and S4. Okay, so first we'll say by looking at the objective function, we decide that x1 should enter to be a basic variable. Okay, so we're going to enter x1 to be a basic variable. But which one we're going to enter? Are we going to switch S1 or S2, S3, S4? We're going to do a ratio test. Okay, we're going to look at the right-hand side. Are you guys done with this? We'll talk about the ratio test. Okay, we're going to put add a column here. Ratio. And this ratio is the right-hand side. The right-hand side divided by the coefficient of your x1, because we're going to switch x1. Okay, so this one equals to be the right-hand side. Okay, the right-hand side divided by x1. We're doing this trying to decide what's the minimum value, or actually what's the maximum value that x1 can be when we switch it into the table. So this ratio is here, and this one equals to b. So we basically just can copy this cell here. It's the right hand side dividing x1's coefficient. So we can copy this. Okay, so we have the ratio here. What about this one? Think again. It's a 5 divided by 0. It's infinity actually. Okay, it's not 0. It's infinity. Okay, so that means so we can still just put it here, but because it's infinity, it's going to be large. We're not going to choose it. We're going to choose the smallest one. Okay, actually I'm just going to put infinity here. Okay. And we're going to choose which one to enter. We choose the smallest. Smallest ratio is 4. So that means we're going to enter x1 into this row here. I'm going to highlight this 2 here. Okay, so based on the ratio test, row 3 wins, and x1 will enter to replace S3. So that means S3 will be switched out to be a non-basic variable. X1 will be in. And the reason we choose the smallest ratio is to make sure later when we solve the problem, when we get the x value, our S1, 2, 3, 4, they are still positive. Okay, if we choose the biggest value to switch, for example, in this case, we switch S1, and when we do the row operation, later the S2, 3 value will become negative. Okay, so just something, no. Okay, now we're going to enter this row. And when we enter this row, the same thing. What we want is, once it's x1 is the basic variable in this row, we're going to make sure its coefficient is 0 in all the other rows and 1 in this row here. Okay, so that's the elementary row operation. So you can copy this heading here. I'm going to copy the row number too. But I'm going to put, okay, I'll just copy in this way. When I work on that row, I'll change it. So the first thing to do is to change the row that x1 entered. To change this row, okay? We're going to put this to be 1. So basically, we're going to divide this entire row by 2. So x1's coefficient in this row is 1. Okay, so we're going to divide it. So our new row 3, I'm going to call it new 3 prime, equals to be the original row 3 divided by 2. Okay, so always put what you do in this row number here, so later you can remind you what I'm doing there. So we're going to put this row 3 divided by 2. Okay, then now you can use your Excel to calculate that. So that because divided by 2. We're calculating the new coefficient for this row. Okay, and then we need to do that into the entire row. I just copy it the other way, including the right hand side value. Okay, don't forget the right hand side value. So right hand side value need to be divided by 2 too, and make sure you change it. Change the basic variable. So the basic variable in this row now is x1. It's no longer s3. Okay, done? Everyone done? Okay, now we're going to look at what do we do. So we're going to change the coefficient in the other rows to be 0. This row is already 0, taken care of. We don't need to do that. Okay, we want to change this one to be a 0. Okay, and we will always use the one that's, because this is 1 now, it's very easy. So we do the elementary row operation. We're going to use this row because it's 1 here, and it's let me zoom it back a little bit. Okay, so now this is negative 60. I want this to be 0. Basically, we'll just use this row multiply 60 and add up to here to cancel this out. Okay, so this row, this entire row multiply 60 and add to this row here. So my new row 0 prime equals to be the 3 prime multiply 60 add to the row 0. Okay, so now this 1 here, this is still 1. Okay, so since we are in Excel, we can just do equations. So equals to be this row here, or let's do this. It's this value multiply 60 multiply 60. Okay, so this row here are the value. So this multiply 60 add up to the original value here. So when you do hand calculation, that's the same step. Okay, now we can just copy this other way. Then you can see we successfully canceled that negative 60 out. 0, that's what we want. All the other value change too. same as the right hand side. Right hand side we need to change, okay? And the basic variable remain to be z. We never change that row. And we don't use the z row to do the elementary row operation either. We usually will just use the row that we just converted the coefficient to be 1. Use that row, that's the easiest. Okay, then you can do the second one. Okay, so in the second row, coefficient is 8 here. So basically we want to use this 1 multiply a negative 8 and add up to that row there to convert this 8 to 0. But when we do that, the entire row will change. Okay, so this 1 prime now equals to be the 3 prime times a negative 8. Times a negative 8 plus the original row 1. Okay, so it equals to be this row times negative 8. Add to the second row. Add to the second row. Oh, sorry, the row number. It is second row, but it's like a row number 1. Add to this value here. Because we're doing the row 1 prime now. Done. Okay. Oh, sorry, did I?
You're fine, just click yes.
Oh, that's the the parentheses there. Okay. Just delete this equation parenthesis here. Okay, so let's go cross it. And the basic variable here remains to be S1. Okay, now then we have just one more left. We want to cancel this 4 here. So we just use this row, multiply negative 4 and add to it. So this new row 2 prime equals to be 3 prime multiply negative 4 plus the row 2, the original row 2. Probably need some better. Instead of like the parenthesis, probably I should use brackets to just differentiate the row. Okay, so you know that these are the row numbers. Those are just actual values. Okay, so here we're going to use this cell here, multiply a negative 4 and add to the row 2, yeah. Because we're working on row 2 now. Get it all the way across. And the basic variable remain to be S2. And for row 4, the x1 coefficient is already 0, so we like it. We don't need to change it. We'll just say 4 prime equals to be the original 4, row 4. Oh, equal, not plus. Okay, then we'll just put a 1 here and another 1 here as 4. Okay, right hand side value is 5. Oh. Right hand side value is 5. So that's our second table. Then from this second table, we're going to write our object function again. So the current objective function z equals to b. Okay, and make sure you because those are the left hand side, we're going to put them on the right hand side now. So add the negative signs on them. Okay, so the z equals to be negative 15 x2 plus 5x3 minus 30 s3 plus 240. Okay, and again we can read all the variables value. They are basically like this. Anything that's not here, and then it's 0. But we're not going to write all of them out this time. What we are trying to do is to see whether we can keep improving our objective function value, which is z here, by switching the basic variables and non-basic variables. Okay, now we know that our x2, x3, they are still not here. So x2, x3, they are still 0. They are non-basic variables. And we can see here, in this, can you see clearly? Should I enlarge it? Can you read it? So now the z is negative 15 times x2 plus 5 times x3 minus 30 s3 plus 240. Okay, and x2, x3, s3, these are non-basic variables, which means their current value are 0. Can we further improve this objective function? We said we want to maximize them. Okay, can we?
Yep. I think we can.
If we increase x2 now is 0. Okay, when we make this positive, we're going to decrease our z value. So that's not working. Okay. What about x3? x3 is now 0. If we make it positive, will that improve our z? Yes. Okay. Then that's one. What about s3?
No.
S3 still get a negative coefficients. That won't help. So x3 is the one that we're going to enter. Okay. So we say x3 should okay. Okay, so we'll just skip a step. We decided now x3 is going to enter. Now we know the next step is to see which one should we switch out. Okay. Then we do what? Ratio test. Okay, we'll do ratio test. And the ratio test we're going to use, because x3 is the one that we're going to switch in. So we'll use the right hand side divided by the x3 value. Not the negative ones. We're not going to use the negative ones, okay? So the negative ones is like a non-applicable, okay? But if it's 0, like here, okay, in the ratio test, if it's 0, we can still use it. It's basically just infinity, okay? So those are not applicable. The positive ones we're not negative ones we're not going to use. Okay, but the positive ones we are. So it's x3. Then we use the right hand side divided by the x3 coefficient, which is this one. Okay. Okay. So which row should we enter? The one that's the smallest. Okay, so x3 is here. We're going to highlight here. Okay, so that means we're going to switch s2 out by increasing x3 value. The objective function value can be improved. Okay, then through the ratio test, it is determined that x3 should enter row 2 to replace s2 as a basic variable. Okay, so that's the and we go to the next one. So we're going to copy this row table again, row heading again. And then we're going to start from we're going to start from the row that's the x, the variable is going to switch. Okay, so that's the row 2. So 0, 1, 2. Okay, my 2 quote now. Now what? I'm going to switch to the bracket. Okay, 2. Okay, so my new row 2 equals to be, now we have a 0.5 here. Remember what's our, you can go, yeah. What's our purpose? What do we want to do now? The elementary row operation. We want to make sure the row where the x entered into as a basic variable, their coefficient to be 0, 0, 1, 0. Follow this format here, so we can solve them. Okay, so we're going to change this one to be a 1, and all the other ones to be 0. Okay, so we'll do this one. So this equals 0.5. What should we do? How do we change the 0.5 to 1? Okay. Multiply it by 2, okay? And then say this equals to be all those values multiply a 2. So this entire row, including the right hand side value. And we are going to change the basic variable to be x3. Okay, now we got this one to be 1. Then we'll just basically finish the other ones. So the x, the first row, it's negative 5. Then we'll just multiply this 5 and add up to it. So this 0 quote now equals to be the 2 quote times 5. Add to the original row prime, or the previous one. So equals to be this row here, multiply a 5, and add 2 here. You multiply by 5, okay, and then go all the way. Then we'll do the second one, the row 1. Row 1 now it's negative 1, so basically we can just add the row 2 quote to row 1 equals to be 2 quote plus the 1 prime. So equals to be this row add up to the row in the previous window here. That's our row 1. Okay. Now we're going to calculate this. And the basic variable remains to be S1. We only switched one of them. Okay, and then one more, a 0.25. So we'll just multiply a negative 0.25 to this row here, this one here, and add to this row. That's row 3. Quote equals to be 2 quote multiply a negative 0.25 and add to the row. The row number is 4, right? See, 0, 1, 2, or 3. Okay, so add to the row 3. Add to the original, so that's the row 3 prime. Yeah. So equals to be this row times a negative 0.25. Add to this row here. Okay. It's simple, but sometimes can be confused. Remember, it's like the previous table. So you use one row from this table and add to the previous table to get this table's new row. Cross. And the basic variable remain to be, oh, actually, x1. Yeah. Okay. And then the last row is 0. We like it. So the 4 would be the same. 4 quote. Equals to be the previous one. 4 prime. So nothing changes. We'll just copy it. It's 1, 1. S4, or you can just do like this equals to be the previous row's value, and drag it all the way down. Maybe easier. Okay. Okay. So we're done with another table. Okay, then next step. What's the next step? Once we have this table, what's the next step? Okay, so we write the objective function again, see if it can be further improved. Okay, so the current objective function z equals to b. And remember to add positive, negative signs to all those coefficients. So equals to be negative 5x2 subtract 10 s2 subtract 10 s3. That's it. Plus the right hand side, which is 280. Okay, now we have this new objective function. I'll enlarge this a little bit. Now we have this new objective function. We look at, we said that those variables in this objective function are the non-basic ones. Okay, and that's why our z equals to be 280. That's because those are non-basic and they're just 0. So this entire part is just 0. But we use this to determine whether we can further improve our objective function value. So we can look at x2 has a negative coefficient here, okay? S2 another negative, S3 another negative, and that's it. So what does this mean? We cannot improve the objective function anymore, okay? And that's our current optimal solution because that's the maximization problem. Okay, do you get relieved? No more table to work. Okay, so that's the last one. Okay, so the current objective function is this one, and it can not be improved anymore by switching the variables. Okay, well, we meant that switching the non-basic ones to be basic. So therefore the optimal solution has been found. Okay, now here we're going to read what's the optimal solution. So we have x1 equals to be what? Can you read from the table? What's the x1 value? x1 table, x1 value 2. Okay, that's because x1 coefficient is 1 here, and you can see 0, 0, 0, 1, 0. Okay, so x1, and it is the basic variable here is 2. Okay, so that's a pretty simple. We can read. So x1 is 2. x2, what's x2 value? Why?
Because it's not one of our basic values.
Good job.
So
Yes,
non-basic.
yes. Okay, so x2 is not listed here as a basic variable, so it means it's non-basic, and the non-basic is just 0. Okay, x2 is 0. x3, it's 8. Thank you. And s1 is 24. So that's not our decision variable, but it's like the slack variable we added. Okay, s1 and s2 equals to be s3 equals to be 0, because these are non-basic too. Okay, then s4 is 5. And the optimal objective function value is, what's the objective function value? 280. Yes, 280. Okay, we read it from here. It's 280, and we can just bring those values back to our model to check. For example, we can check it here. Okay, those are all 0, that's why it's 280. And we can bring all those values back. So our x1, 2, so the original model here. So once you have the problem solved, different ways to validate if your model is, like your result is right. You can have use the solver to solve it, but if it's an exam, you won't have that way. So you can just put them back to your to your model. Okay. Oh, did I copy it here? Right. Oh, okay. So it's yeah. So basically, we can just put it so that make it equals to be 60, okay, times your x1 value plus x2, we know it's 0, plus 20 times your x3 value here, 8. Yeah, so it is 280. That's the value we got for here. So that's one way. And you can also plug those x1, 2, 3 value back to your constraints to see if they are right. And also like the S1, S2 values, so plug all of them in and they should be all right. Okay, and we mentioned that if you had, when you find the optimal solution and you found the sum of those S, the slack variables are negative, what does that mean? If you have a slack variable that's negative, can they be negative? Slack variables? No, they can't. If there's a negative slack variable, that means error in your model. Okay, you violated one of the constraints, 1 or 2 of the constraints. Okay, and many times if you didn't do the ratio test right, you may have the you may have a negative slack variable. Okay, so that's the simplex using only less than equal to. Okay, so we convert it. We put all those values, all the coefficients in the table, and we write the object function to see whether by improving by switching the non-basic variables to be a basic variable, whether we can improve our objective function. This one is maximize. If it's a minimization problem, then here we're already done. If it's negative, if it's a minimization problem, because these are all positive. Okay, so if the problem switch to be a minimization problem, then you can think about the same way, just opposite. If those are all positive, then that means the problem is done. If you still have negative coefficients, then that means by improving those decision variable values, you can still decrease your object function value, which further minimize the problem. Okay, and then you do the ratio test to determine which row that the specific decision variable should enter. Okay, now we'll do this one quickly. This one should be pretty simple now. We'll just put it. Okay, so I'm sure you won't be able to do it in 4 minutes, but we'll just convert this one. Convert this one quickly. So remember, we convert the objective function too. We add a z there. So we minimize z, which equals to be this, right? And we we add the select variables. So we'll have 2 select variables, okay? We'll minimize z equals to be 2x1 minus 3x2, and we add 2 select variables, and make sure you add those select variables to your constraints, make them greater than or equal to 0. We'll ask you to create a new spreadsheet, or just finish it next time. Create the heading of it, if you remember. What are the headings that you need to include? So we need to have the row number,